Welcome back, physics fans. This is Physics 11's Projectile Package, page 12, and we're doing question 23. This is Kinematics, Physics 11. A golf ball is hit at 25 meters per second at an angle of 20 degrees above the horizontal it'll be. You're hitting it upwards. How far does it travel before landing on the ground, assuming no hills? So it does a shot and lands, and the original shot is at 25. So 25 meters per second at an angle of 20 degrees. So what we're looking for is the vertical component and the horizontal component. And using your trig, this is 25 sine 20, and this will be 25 cosine 20. Okay, pulling up Mr. Calculator, and let's try that out. That's going to be 25 sine 20 and 25 cosine 20. Getting the two values. Pardon me, sorry. 8.5505, and this is 23.492. Okay, so we now start filling in the tables because we have a lot of data. So the gravity is down at 9.8. The initial velocity is 8.5505. 8.5505 up, and the horizontal speed is 23.4292. If you want, put it horizontal. Do we have any other pieces of information? We have actually, surprisingly, a couple more. It is that initially, if it's landing over here, it's coming in and landing down here and hitting down at this point. That's the vector down there. Its displacement is 0, because up and down it comes back at the same place. And in Mr. Curlism, what goes up must come down and at the same speed. So 8.5505 down. The change in velocity is going to be 2 times 8.5505 up and down. Add them both together if you want, and divide it by the acceleration of 9.8, and that gives us the time. There's lots of different ways to do a time, 3 different ways, and I'll just do this one. So I'll take that number, multiply it by 2, and divide it by 9.8. So the time of the flight is 1.745 seconds. Okay. 1.745 seconds. And then we're trying to find out the range. And the range is just another term for the horizontal distance. And that's going to be velocity times time. And that is 23.492. And we multiply it by 1.745. And we get the range. So we take this number and multiply it by that number, and we get the range. 40.994 meters. Dun, da, da, dum. Thank you very much. Any questions? Well, let's do a little bonus part to it. Part B. What final velocity does it land at? The final vertical velocity is 8.5505, and the final horizontal velocity is that. So if we want, draw the triangle. 23.492, and this is 8.5505, and now we want to find the hypotenuse. Yes, I know some people are itching and saying, I know the answer, because there's a pattern here. But let's pretend we didn't see the pattern. And let's be odd when it comes up. So I have to take that squared and that squared, add them together, and then square root it to get the hypotenuse because of Pythagoras. So we take that squared plus the 23 squared, and it's 625. Ooh, exactly 625. That's just, oh. And then if we square root 625, we get exactly 25. Wow, exactly. And that only happens if you keep more than 5 sig figs. That's what I was doing. I was keeping more since I was using all 9 or 10 that are here. 25, exactly. Okay, what's the angle? Let's take that number divided by that number and inverse tan. Because the tan of theta is the opposite over the adjacent. ADJ. Opposite is 8.55 number. The other number is the 23.492 number. You divide that, and that's going to be the tan. So to get the angle, we have to inverse tan. So theta is going to be the inverse tan of 8.55 all divided by 23.49. So we divide them and then inverse tan. So we do the inverse tan of the 8.55 number, way up here, the sign, here it is, divided by the 23 number, there. So the 8 and then this, and close the bracket, and we'll get a cool number here. Exactly 20. Huh? VF is going to equal, I'm sorry, theta is 20 degrees here. So VF, the vector, is going to be 25 meters per second, and the angle is 20 degrees BTH, below the horizontal. And that's the final. Here's the aha moment. If you haven't been there yet, and I'm sure a lot of you are there, it was launched at 25, at 20 above, it comes back down. Exactly the same amount, but 20 below. Why? Well, the horizontal is the same, and the vertical is just swapped. So this triangle and this triangle that we started with are identical, except it's upside down. So it's going to be identical. They're exact same triangles, not just similar, exact. So when something is on a level ground projectile and it lands at the exact same velocity, two-dimensional velocity, as it is launched. Of course, and that's in perfect physics world with no friction. Thank you so much. I hope you enjoyed that.